So your module 5, your first module in year 12 is on equilibrium. And this concept relies on the fact that you need to certainly meet conditions first. The conditions you need to meet for equilibrium are that you must have a closed system, as well as you must have a reversible reaction. Now, in case anyone is confused about what these mean, whether your system is open or closed, your system can be 3 types. It can either be open, closed, or isolated. And I'll go on the next page into different types on that. And reversible reactions, it should be quite clear to you what these are at this point. But basically, if we think of it simply, we then say either the reaction is, complete, or no reaction being the 2 extreme, or reversible. But of course, everything is reversible to some extent. In fact, let's do it here. Whether a system is open or closed or isolated basically refers to whether it's allowed to exchange matter or energy with surroundings. So from an open system, then both matter and energy are able to be exchanged. So think of it like an open cup. That's an open system. It can become hotter, it can become colder, water can evaporate and leave, and that's an open system. But a closed system will be perhaps if you put a lid on it, so the matter cannot escape, but the energy can. Or if you've got a bottle, you heat it up or cool it down, but you can't take anything out of the bottle if it's got a lid on it. And an isolated system is one where neither matter and energy can be exchanged, and that's relatively rare and is never true in the real world, but it's sort of getting closer to true if you're looking at something that's very, very far away by itself, like, a star that's not related to anything, or a planet, or something like a bomb calorimeter. Okay, so that's your sort of system classification. Your reversibility of a system, remember, depends on whether if it's a complete reaction, such as combustion. And the point of this is 100% products and 0% reactants. That's ideal. Or if something doesn't react at all, such as if you have hydrochloric acid and gold, which basically doesn't react. Or if you have something that, like, if you've got copper plus magnesium sulfate, that again basically doesn't react. And that's when you have 100% reactants and 0% products. Nothing reacted. And then, of course, you've got things in the middle, which we call a reversible reaction. And this is when you've got some level of products and reactants. But this is, not 0%. And this is despite given as much time as you want, they both still exist. And your typical example might be the Haber process. Right? So basically on the left, reaction doesn't happen, and it's just reactants. On the right, all products. And in the middle is sort of your reversible reaction. And as a foreshadowing of the revision to come, quantitatively, this side is basically very high K, equilibrium constant. This is very low K, equilibrium constant. And this is sort of in your middle. Typically for chemical equations, we're looking at around 0.1 to 1,000. But remember, K is a number. So, it simply represents where on the scale you are. So we need something that's got a reversible reaction, and we need an open system. And then as long as that is there, we'll be able to reach equilibrium. Then it can reach equilibrium. Now, what do we mean by reaching equilibrium? Well, then we can say that if a system is at equilibrium, then by definition, and this is where equilibrium comes in, that means the rate of the forward reaction must equal the rate of the reverse reaction. But very importantly, these are not zero. In other words, the reaction is still occurring. Both in the forward and the reverse direction. And this is often abbreviated to R1 equals R2 not equal to 0. So if something is at equilibrium, we say the forward rate equals the reverse rate and it's not equal to 0. And the second thing we can therefore say is that despite that, macroscopic properties are constant. So macroscopic properties are basically any property you can measure at the system level. So, you know, basically system properties. So we're basically saying, unless you care about the actual, which molecules are where, anything else you can measure about the system as a whole is constant. And your typical ones, of course, will be, you know, your concentration, temperature, pressure. But when we say macroscopic properties, it's basically anything at all that, you know, that doesn't measure purely at the atomic level. Anything overall will not change. Constant means they'll, you know, not change. So you can look at concentration, temperature, pressure. You could be looking at the mass. You could be looking at the density, color, so forth. Okay, it doesn't matter. So that will allow a system to reach equilibrium. And the reason that you need a closed system is so the matter doesn't escape. You need a reversible reaction is because that means, you know, the forward rate and the reverse rate can equal each other. Now note, because it's not equal to 0, we call this a dynamic equilibrium. In other words, it is still occurring. So equilibrium more generally, there are dynamic and static ones. In chemistry, we don't really focus on the static ones because they're not really relevant for us. But the reason why we call them a dynamic equilibrium is because of the fact that it still occurs. So once a system has reached equilibrium, then what that then means is, well, as we said earlier, its macroscopic properties are unchanged, so concentration is a constant, and the fact is that its forward rate equals the reverse rate. That then means that you can now disturb the system. In other words, make some sort of change. Now, if we're going to be looking at these things sort of qualitatively for the moment, then if you disturb a system, in other words, you make a change, then what that means is you will need to use, qualitatively, you will use Le Chatelier's principle. And what Le Chatelier's principle says is that, think of it like sort of, you know, friction or anything that kind of, it always goes against you. So whatever change you made, it will go against you. So basically it will be opposing or minimizing the disturbance. Whatever you did to the system, it will want to go against you. That's what we're saying. So it will do that, and then the result of that will be you will reach a new equilibrium. And we'll give some examples perhaps on the next page, hopefully, to sort of quickly revise this. But you can make, if you've got a system at equilibrium, and obviously, you know, it needs to meet the conditions to meet equilibrium. So, you know, if it's a complete reaction, then this is not relevant. But if you've got a system at equilibrium and then you make some sort of change to it, temperature, pressure, concentration being the typical examples, then use Le Chatelier's principle. That will then it will then go against you to minimize the disturbance. Now, remember, the choices the system can do are only two ways. It can either choose to either go to the right or go backwards. And whatever way it goes, its aim is to try to go against the change. Now, note I said minimize the disturbance. That means reduce the disturbance. I never say get rid of, because it can't. It will always try to minimize it, but note the disturbance will still occur. But it will simply be lower. All right. So this is Le Chatelier's principle, system at equilibrium, you disturb it, and then you reach a new equilibrium. And so what changes could we do to it? Well, examples of the change. And basically you will apply Le Chatelier's principle. Remember, it's always use Le Chatelier's principle. So, you know, what is opposite to the change? And then think of how this would be achieved, and then think of the shift. So typical examples are add reactant. Opposite to the change will therefore be reduce reactant. And that would be, in other words, shift right. You know, you would basically use the forward reaction to use it up. Obviously, very similarly, remove reactant will be, you know, add reactant. Well, you can't add, but you would, you know, increase reactant concentration. And that basically pushes the reverse, and that will be shift left. And very similarly, if you add product, then it will reduce product. And that means it will push the reverse, and that will be shift left. If you remove product, that means you would want to increase product. That means it will push the forward. That means it will shift right. Now, with these four that I've just mentioned, if you're going to be adding or removing product, note that these are really only useful if it affects concentration. So really we're talking about gases or solutions mainly. If we're adding or removing solids, we don't care. It doesn't affect reaction rate. It's not going to affect equilibrium. Okay. Keep that in mind. That's one thing you might want to watch out for when you're doing that. And you do need to basically pay attention to concentration when we're doing these things, as well as when you do the equilibrium constant, and that will come up in a moment. Remember, focusing on concentration. So those are adding or removing products. And then your other typical examples are if you increase temperature. Now, if you increase temperature, that means you will want to reduce temperature. And just kind of like in the same way that if it's summer, if it's hot, you want to turn on the air conditioner, the system will want to make it colder. And it only has two choices. It either goes forward or reverse. Now, without giving you an example equation, you won't know which is which, but you do know that it wants to make it colder, which means it will push the endothermic reaction. And that will just depend on the equation, all right? So basically towards, delta H is positive side, whichever side that is. So if you're decreasing temperature, then it will try to increase temperature. In the same way that in winter, you'll want to turn on the heater. So it's really cold now, the system want to increase the temperature, and it does that by, well, making more heat, releasing more heat, pushing the exothermic side. So that will be towards the side where delta H is negative, whichever side that is. It will depend on the reaction. And your other typical examples are increasing pressure. And this simple example like this is basically the same as saying decreasing volume. They're really the same. And we could also, that means the system can't really change volume, right? You decide volume because you decide the container size and how hard to push. So decreasing volume really is the same as increasing pressure, at least by changing volume, which means the system is basically, in both cases, going to try to decrease pressure. How do it achieve that? Well, it would try to shift towards the side. So it's kind of like, you've got less space. If you've got less space, you want to kind of pack things more efficiently. And it's a bit like, if you've got a certain number of boxes, if you have less boxes, you just, put things more tightly into fewer boxes. So you would shift to the side with less moles of gas. And again, that depends on your reaction. If you were to decrease pressure, that would be analogous and the same as if I did it by increasing volume. And the system will therefore try to do that by increasing pressure. And it will do that by shifting to the side with more moles of gas. Okay, so these are the ones that are frequently tested. I've more or less separated them into, add or remove product or reactants, increasing or decreasing temperature, okay, increasing or decreasing pressure. Now, just like with adding or removing reactants, you really want to focus on concentration. Pressure, again, also really only affects concentration if it's a gas. So this really is only relevant for gases. Again, if you've got a reaction that doesn't have any sort of, if you've got a reaction that doesn't have any gases involved, then it's not going to really affect equilibrium. Okay. So yes, I've mentioned that earlier, but just reiterating again, that if you add or remove a solid from a reaction that is in equilibrium, because it does not affect concentration, it will not affect the equilibrium. Yeah. Does that answer your question, Lauren? Okay, good. So let's continue. So these are the common ones, and these are the sort of easy ones. Now, just note that sort of variations, all right? I'll do variations on the next page. So variations on that sort of theme include adding, you know, a substance that is not a product or reactant. Now, you know, if you add a substance that is not a product or reactant, basically there's two choices here. One is that it doesn't affect the reaction, which is probably not going to be the case, the choice you're going to go for, because it's there for a reason if they're asking you, right? So in real life, if you add something that's not a product or a reactant, then you know either it's not going to affect it, but that's unlikely for an exam, because why would they be asking you? Or more likely for your exam purposes, it's going to affect it. But if it does affect it, but it's not a product or reactant, that doesn't really make sense. Unless, and this is what the important part, you need to figure out, work out, understand what adding that substance does to one of the products or reactants. Yeah. You need to understand what adding that substance will do to one of those products or reactants. So I'll just give you some examples, quick examples here, because this might make it clearer here. So if I already have an equilibrium, such as for acetic acid, which is a weak acid, with water, and I'm going to get CH3CO plus H3O plus, and now my change is I add NaOH. Now, if we add sodium hydroxide, sodium hydroxide is not any of these four things, so it falls into the category. I'm adding a substance that's not a product or reactant. However, you guys should hopefully know that this is a base, and this is the acid. And so you should note that NaOH, if we're sort of writing out the steps a bit more, NaOH aqueous is really Na plus OH minus. But OH minus will not just sit there doing nothing. OH minus will react with H3O plus to form H2O. And, just in case there's any confusion, H2O is a liquid, not a solution, it's a liquid. So unless, you've got special cases that I haven't really talked about and you generally won't worry about, as I said, you care about gases and aqueous solution concentrations because the liquid concentration doesn't change, just like a solid. So we're not affecting, we are affecting the amount of water, but not the concentration of water. So we don't care. It's not affecting this. What it is affecting, though, is this. The hydrogen ion concentration goes down because it's being used up. The more OH minus you add, the more it will react. The more that reacts, this goes down. So what I'm basically saying is, this question saying this is another way of saying H3O plus goes down. And so our argument in very short terms is when we add NaOH, it will neutralize based on the above. Therefore, H3O plus will go down is the change. This is the change, basically. And if that's the change, then by LCP, saving sort of writing here, but for an exam, do not do this, write out the whole thing. By Le Chatelier's principle, you want to increase that. you want to make this go up, and that basically means shift right. All right, so this is one example of that. Plenty of other examples, but basically it will either not affect it, which is unlikely for an exam, or you have to figure out what on earth is going on when you add it. Okay. So alternatively, you might have example 2. If you might have something like lead sulfate, solid. You understand that this is relatively insoluble. I'll pick something that's more equilibrium, I suppose. But it would have been fine, but let's pick an even better example. So lead chloride. You understand that this can form a saturated solution, and that would in and of itself be an equilibrium. And so let's say now I add sodium chloride. Either solid or liquid, or aqueous, it doesn't really matter. If it's a solid, it will dissolve. So note that if you add NaCl aqueous, what that means is you'll get Na plus plus Cl minus. It will dissociate. So really what we're doing when we're adding NaCl aqueous, in other words, I mean, it is, I guess it is not technically lead chloride, it's not technically lead ion, but hopefully this one's quite simple to see that you are adding chloride ion basically, right? So you'll notice that basically you're adding chloride ions, that's the change. And that basically would therefore mean that, the system will want to bring down the amount of chloride ions by LCP, which means it will shift to the left. Now, shifting left for this sort of equation, you might want to express that differently, depends on how the question's worded, but this is a solubility thing. So you might notice and recognize that to the right here, this is dissolving. To the left here, this is crystallization. So in other words, more to the right is more soluble. More to the left is more precipitate, so less soluble. So another way to describe this is talking about shifting to the left, meaning that, it becomes less soluble. And this is pretty much just a qualitative demonstration of what you've already learned and have examined quantitatively as the common ion effect, right? So that's variation number 1. There are some other variations that are less likely to be tested, but I should, briefly mention. So other changes include adding an addition of catalyst. And the answer to that is quite simple. If you add a catalyst, what a catalyst does is it reduces activation energy from E11, which means that you both forward and reaction rates will increase. So to increase reaction rates, but they both increase. But they go up by the same amount. Which therefore means there is no effect on equilibrium. That one is, actually quite commonly tested, and probably should have put it in the common table, but because there's no sort of change, I didn't put that in there. But basically, another option is addition of catalyst. And if you add catalyst, the answer is, as far as equilibrium is concerned, is always no change to equilibrium. The next 2 are less likely tested, but I'll briefly go through it with you. I won't go into too much detail because I want to get onto other things, but just, and because they're less commonly tested, but if these 2 confuse you, then don't worry about it too much. They can come up, but relatively rare. So what we could do is we could also keep volume constant. So these are for gases. So you keep the volume constant, but you increase pressure Now, if you keep volume constant, the only way to increase pressure is by adding gases. Now, if you add gases, then you're either adding a product or reactant. And if you're doing that, then just answer the question based on if you're adding or removing a product or reactant. Just do it that way. But here, we don't add a product or reactant. So we increase pressure by adding a gas that is not a product or reactant, and more technically, we'll make it even easier this is harder, but easier out of the harder, that is inert. In other words, does not react. So in other words, e.g. helium. So I'm telling you that it doesn't react. And because I'm telling you it doesn't react, then your job's a little bit easier, because I'm telling you if it doesn't react, it means that it's, well, clearly not going to, not going to do anything with the product or reactants. And that's one of the things you need to worry about, okay? If I don't add an inert gas, you need to worry about it, but then I don't think they'll ask you that, all right? But I'm adding an inert gas, which means, either it's not going to affect it, or it's, well, not going to affect, it's certainly not going to affect any of these, any of the product or reactants for any reaction that we will ask you. So if you keep the volume constant but increase pressure, then basically the partial pressures do not change. And so the final result is no change in equilibrium, no shift in equilibrium position. Okay. Now, the other one is if you were to keep pressure constant, but we will increase our volume. So you basically make your container bigger. Now, generally speaking, if you make your container bigger, the pressure will drop, okay? But since we're keeping pressure constant, how do we do that? Well, we will by adding an inert gas, such as helium, to maintain the constant pressure. Now, because what you care about are your, rates of reaction and your sort of your reactants or products, or your forward rate and reverse rate, when you increase the volume, even though you kept the pressure constant, this is total pressure, but the partial pressures have dropped. Partial pressures just basically refer to the pressure of each sort of, substance, and they do drop because you're increasing volume, because, pressure equals N over V, right? So as you're increasing, well, it's essentially concentration really, but concentration equals N over V, and you're essentially decreasing concentration. So therefore, there will be a shift towards the side with more moles of gas. Now, as I mentioned before, these two are relatively less likely tested. So don't worry too much if you have, if you're not as clear on these two, but they can be, but are less commonly tested. So that basically covers equilibrium from a qualitative point of view. So far, we've looked at equilibrium qualitatively, and you should have a good understanding of that. So that basically tells you how to do things, in terms of like which way it's going to go. So you have qualitative analysis, and that's basically your observations, like which way will it shift. And we basically just rely on LCP for that, and your general sort of observations when you do experiments. Now, the other thing then is we're going to do quantitative analysis. And basically that relies on us to do calculations. So not only which way will it go, so not just which way, but also exactly how far will things shift, and which way. And this basically relies on the concept of K, called the equilibrium constant. Okay, so what is K? Well, K is the equilibrium constant. And it depends on the reaction. So whenever you talk about K, you understand it's an equilibrium constant, but it is different for each and every reaction. So if we consider AA plus BB in equilibrium with CC plus DD, note that the equilibrium constant is going to be calculated by, now, most students remember that you're going to need to take powers, but one common mistake is that they'll do it the wrong way around, right? They'll, get mixed up between quotients, the numerator and denominator. So I don't want you to sort of memorize it as, oh, what the letters are. I don't think, unless you feel that helps you more. Basically, conceptually, you need to understand that I've mentioned before that K is trying to tell you how complete a reaction is. If you remember what we did earlier in this lesson, we said basically that the bigger the K, the more complete, which means, more products, right? Basically, and less reactants. And you should definitely understand that, K needs to go up for this side. So this is like a complete reaction. And so for incomplete or no reaction, I should say, then we've got K small. And then you've got, equilibrium, which is like K in the middle. Now, we've said that K in the middle is roughly 0.1 to 1,000 approximately. K small, it's just a number, but, you could have something like K is like, 10 to the negative 7 or smaller, like 11, 20 even. And this could be like big. This could be like, K could be like, 10 to the power of, 6, 10, 20, 30, depending on what type of reaction I'm talking about. So you can see there's a massive range here. But the key point is, if you're going to get K big, then that's meant to happen when products are more than reactants. And for K to be big, one of them go on the top, one of them go on the bottom. So if you ever get confused, then basically just link all of this together and think of it as products over reactants. It's basically some sort of expression giving you some sort of idea of how many products there are versus reactant at equilibrium. And given that, we would then take C to the power of C and D to the power of D over A to the power of A and B to the power of B. So the things to watch out for are, make sure you know which is which. So products over reactants. The other very common mistake, most people, know, C with C, D with D, and so on, and they get the power and all that. The other very common mistake is that they forget to use concentration. These brackets, hopefully mean concentration. So you need to use concentration. Now that means two other common mistakes. So one is because you're using concentration, as we said earlier, before, you ignore solids or liquids usually, right? Because they don't have concentrations that change. And so we basically ignore them usually in our equilibrium constant. And the other mistake is if it's a gas, then we need to use concentration, not number of moles, okay? A question might be made more difficult. They might tell you that you've got, 3 moles of gas in, a 10-liter container. Then your concentration is not 3, but 0.3. And so when you work out your equilibrium constant, you might make that mistake, okay? So whenever you're working with the equilibrium constant, pay attention to and gas, and have you converted them to concentration as opposed to keep them in number of moles? Are they different? If it's 1 liter, then it's the same anyway. But if it's not 1 liter, then you'll need to change it. Okay. Now, this K is for this reaction. So note that when I say K, value of K depends on 2 things. On the reaction, and by that I mean both the direction. So because it's reversible, I could write it as AA plus BB to give me CC plus DD. I could also write it as CC plus DD to give me AA plus BB, but then I'll get a different equilibrium constant. So it depends on the direction, and obviously it depends on the coefficients. So maybe I would write, 2A plus 2, 2AA plus 2BB equals 2CC plus 2DD. Depending on if I use fractions or whole numbers, that could change. You could see in your reference sheet, sometimes you use fractions. And if you change the whole numbers, then K will change because the powers will be different. So be careful with that. And if they didn't give you a reaction, then, assume whole numbers, okay? Assume whole numbers and that you didn't use fractions. And the other thing K depends on is temperature. But once you know those things, then the key point is, if these things are set, then K does not change. And that's what makes it useful. So just quickly reiterating how, examples of how K might change. So if you have a reaction, so K may change based on 1, obviously the reaction, so different reaction is obviously different K. 2, the direction of the reaction. So if I have, AA plus BB to give me CC plus DD, I'll leave off the states to save time, versus CC plus DD to give me AA plus BB. Note, if this has equilibrium constant of, K, 1, then this K will equal 1 over K1. You can show it algebraically, all right? I'll just go directly to the results. Now, it might depend on the coefficients. So if you've got AA plus BB to give you CC plus DD, and I multiply everything by, say, M, so I've got MAA plus MBB to give you MCC plus MDD. If this equilibrium constant is K, then this one will be K to the power of M. And then the other thing that it may change on is based on temperature. For your purposes, we will talk about this in a moment, but you do not need to know this quantitatively. You only need to know the direction in which the K will change. But there is no need in your course to calculate, the new value of K based on the temperature change. There is a way to do it, but you don't need to know it. So that's how K might change. But the important thing, as I said, was why equilibrium constant is useful. The important aspect is if these are set, then we know that equilibrium constant will not change. So if the above is set, then K will not change for that reaction at that temperature. All right. So remember K, the value we've mentioned already. If K is large, that basically indicates a complete reaction. If K is small, that indicates sort of no reaction. If K is in the middle, then it indicates a equilibrium or reversible reaction. Now, we also want to distinguish how is this helpful for us? Well, basically, to quantitatively, determine shift, or to qualitatively determine shift to start with, but using, qualitatively determined equilibrium shift, we basically calculate Q, and then secondly compare to K. So remember, K is an equilibrium constant. So the K and Q are basically the same thing. So note Q is called the reaction quotient, and K is called the equilibrium constant. Now, they are different in a sense, but basically, let's take an example of a reaction, N2 plus 3H2 to give you 2NH3. Now note that, Q and K are both calculated by, NH3 to the power of 2 concentration over H2 to the power of 3 times N2, okay? They're both calculated the same way, but there is a critical difference. K is only using the concentrations once equilibrium is reached. Whereas Q is concentration at a particular point in time. So the point is, K for a particular temperature and reaction is set. Like, let's say it's 100. Let's keep it simple. K is 100, all right? So unless you change the temperature or you change the reaction, K is 100. You know that. But that means that that's the number you get if you sub in values at equilibrium. Q, on the other hand, you just sub in the numbers at any point in time. So you don't know that if Q will be 100. You don't know that. But you can calculate the value at any point in time, even though, you can just take some measurements and calculate it. So if you calculate Q and it equals K, well, what that basically tells you is that your system is at equilibrium. Now, if you calculate Q and it doesn't equal K, well, then, it tells you it is not at equilibrium. And then really, there's two options here. One is that it's bigger than K, and one is it's smaller than K. Now, obviously, I could just tell you which way it shifts. But I think, again, many students, depending on how well you know in theory, you can obviously just memorize the shifts, but I don't think it really helps you because you then might be in the exam, if you're not clear on this, go, well, I know it was one of them, but I don't know which one, so it's kind of 50-50 and I'm a bit confused. So what you need to understand is that, if Q is not equal to K, it's not at equilibrium, but it means it will go towards equilibrium, right? The system, if you're not doing anything to it, if you're leaving it by itself, it will go towards equilibrium. So over time, Q needs to go to K. So if Q is bigger than K, because Q will need to go to K, that means Q needs to now go down because it's currently bigger. And if Q goes down, we're saying that this quotient goes down, and that hopefully, based on what we said, in the previous slides, helps you understand why this means that it must shift left to reach equilibrium. Now, if Q is smaller than K, that means ultimately, as before, Q will need to basically go towards K to reach equilibrium because, you're letting it reach equilibrium. But in this case, Q needs to go up to do that. So that instead means that we're going to be shifting to the right. So that's how you use equilibrium position to sort of calculate what you're going to do with that, which way will you need to shift. You calculate Q, compare it to K, and then basically it's either equal, which is at equilibrium, or it's either bigger than, which means it needs to become smaller, so shift left, or it's smaller, so it's bigger, shift right. Okay. Now, that's with your K, with your shifts. We also need to talk about K and temperature. Now again, so note, K changes if T changes. Now, again, just like K and Q, we could just tell you, okay, if this, if that, then this, like just, direct a result. And if you're comfortable with that and you have no problems with it, great. But it might help to sort of think about this from a qualitative point of view with Le Chatelier's principle. So if we increase temperature, remember that the system will want to decrease temperature to oppose the change. And that means it will favor the endothermic reaction. Now, that means, so that's in general. So let's take a look at a equation. For example, a very typical one might be, say, N2 plus H2 to NH3 gas, and this is going to be exothermic. So we know from quantitatively that this is going to shift up, which means temperature goes up, temperature will go against that by favoring the endothermic. So in this case, in the example above, then it will, shift to the left, or it will, favor the left-hand side, which of course means that the shift ultimately will be towards the left. All right. But we had to use this example above, and we knew it shifted left because of the fact that this reaction here is exothermic. Now, if you shift left, what happens to K? And if you think about it, going left means K went down. So conversely, if we decrease temperature, the system will increase temperature, and that will favor the exothermic reaction, which in our example here would favor the right-hand side. So which means it will shift to the right, which means K will increase. Now, of course, you might not have an exothermic reaction. You might have an endothermic reaction. And that's why what happens to K depends on if your example is endothermic or exothermic. So here, in our example, which was exothermic, this is what happens. But if our example was endothermic, then you'll see that the effects change. So increased temperature means you'll want to decrease temperature. It will obviously favor the endothermic. But if we have an endothermic reaction going to the right, that means it will favor the right, which means it will shift right, which means that K will go up. So if it goes down, then it will increase temperature by favoring the exothermic, which means it will favor the left in this example, which means it will shift left, so K will go down. So what you are asked to often do is just predict in a multiple choice question, for example, okay, we made a change, the temperature went up, here's a reaction, what happened to K? So you can skip all of this if you like and just go, well, it's exothermic, temperature up, exothermic, so K went down, right? You can do that if you're comfortable with that. But rather, if you forgot or get confused, you can kind of just basically work it out based on what we've said before, right? So, temperature went up, So you want to decrease the temperature, which means that it's, you know, and you'll push the endothermic, and in this case, that means shift left, so that means K will go down. Okay. So that's K in temperature. And, you know, basically everything here we say about equilibrium is really going to be is going to come up a lot in your course. So we've talked a bit about, you know, KSP, which is in your module 5, but it's also in your KA. So sort of applications. So, I mean, I won't stick strictly to module 5 here. So applications of K obviously include your, you know, KEQ for your chemical equilibrium in your chemical reactions. You've got your KSP, which is your, you know, solubility product. So, you know, you can think of these as separate things if you like, and they're often stressed as separate things, but they're all the same. It's an equilibrium constant. So, right, it's a solubility product, right? That we'll talk about in a moment, but basically this is a measure of solubility using K to do it. You know, you've got your KA, you've got your KB in module 6, right? You know, you've got your KW, again in module 6. So there's a self-ionization of water, which is, you know, roughly 10 to the negative 14 at 25 degrees Celsius. And that is, you know, underpins your definition of pH, right? But basically this is just the equilibrium constant for, you know, H2O plus H2O to give you, you know, H3O plus OH minus. And that's why KW is just H3O plus times OH minus, because these are liquid, you don't care, right? It's just the same thing. Ka is basically just, you know, your, you know, it represents the strength of an acid. And this represents the strength of a base. And basically it gives you the sort of the degree of ionization using K to do it, a quantitative measure, right? Degree of ionization or dissociation. So, you know, you can apply K, you know, across your course multiple times, right? And but it's all the same. All the rules we've kind of covered underlie, you know, all of those, because ultimately they're equilibrium constants, all right? So we'll look specifically at KSP, and this is, you know, more or less the last thing we need to sort of look at before doing questions specifically. So solubility product, or otherwise known as KSP. Now, we can talk about this, you know, as like a separate thing, but we've more or less already covered it, honestly. So this basically is just calculating the K for a reaction with regards to it's calculating the K for the reaction that is a dissolution of an ionic compound. So, you know, if you've got something like XY, where X is your cation and Y is your anion, when it dissolves, it will become, you know, X plus or 2 plus or whatever, right? Plus Y minus or 2 minus or whatever, and, you know, do the ratios appropriately. It's not important. What it's important is that solids on the left, aqueous is on the bottom. And now, when I say it's not important, I just mean that you can do it for the appropriate one. All right, I'm doing a general case here. Obviously, the coefficients are important for your K, all right? But then your K is basically just going to be your X plus in my example here, times your Y minus. Notice that this is a solid, so who cares? And so this is our K. But given that this is a, you know, dissolution of an ionic compound, then we, you know, you might be, you know, specifically labeling this as KSP. But it's just a K. I mean, there's no difference there. All right. And, you know, if I had something like, you know, X2, you know, X3, Y2 as an example, just in case there's any confusion, you know, then of course that would become, you know, this most likely would be like 3x2 plus 2y3 minus. And of course, this KSP will of course be, you know, x2 plus to the power of 3 plus y3 minus to the power of 2, all right? And you can quite clearly see that it literally is just our k, but, you know, we've just, you know, been doing it with ions this time. There's nothing really new here, all right? Even if you've been doing it as a new section. And again, nothing's really new in the sense that, you know, so KSP high means it's, more generally, it means it's, you know, equilibrium to the right, lies to the right, which means it's soluble. And that's why we say KSP high means it's soluble. And obviously KSP low means its equilibrium is to the left, which then just basically means it's, you know, not soluble or, you know, relatively insoluble. Now, of course, if your KSP is in the middle sort of section, then of course, then it's sort of like it's in the middle, obviously. And that's kind of like sort of soluble, like slightly soluble. And this, you know, so the KSP values, you know, are not the same as the K values in the sense that, you know, we're talking sort of smaller ranges here. So, you know, usually we might say that if it's 10 to the minus 3, so kind of like 0.001, then it's kind of on the borderline of, you know, but yeah, just basically I'm saying it doesn't matter too much about the ranges specifically because ultimately just a number. Now, note that for any KSP that you need, KSPs that you need will be on the reference sheet. So anytime you need to do any sort of calculations, then, you know, you'll do the reference sheet. All right. Speaking of the reference sheet, let's talk about the common ion effect and then do it, you know, I'll make up a question while we do it. So let's say, what's the common ion effect? Well, this is basically just a fancy name that you can use if you're trying to describe things to basically say that the solubility of an ionic substance, you know, will decrease as, you know, concentration of ions increase. You know, that are common ions increase. And it's hopefully quite clear why that's the case if it's not clear already based on what we said before. But basically, you know, if you've got something that like, you know, lead chloride, for example, I think we did use an example like this earlier, but it applies to basically all your, you know, equilibrium solubility. So it will establish an equilibrium like this, right? It will establish an equilibrium like this, which means that, you know, your KSP will equal lead 2 plus, in my example here, times chloride squared. And this will be constant at a particular temperature. So we've noted that, you know, K depends on temperature, then so clearly KSP will also depend on temperature. And your solubility constants at 25 degrees Celsius are on your reference sheet. And if you look that up in the case of lead chloride at 25 degrees Celsius, you'll find that's one of the more soluble ones on the reference sheet, relatively speaking, and that's 1.70 times 10 to the negative 5. And also, just another sort of exam technique point I might want to mention here. You are meant to know solubility rules from year 11, okay? And if you know them, then great. If you don't know them, we'll try to revise them. But your solubility rules from year 11 will tell you that all chlorides are soluble except for, you know, silver, lead, and mercury. So your solubility rules from year 11 tells you that this is not soluble. And your KSP kind of tells you that because 10 to the minus 5, while it's one of the bigger numbers on the reference sheet, it is relatively small. Like, you know, you're talking about 0.00, you know, 0.017 or something like that. So you've got quite a few zeros there. So it's quite insoluble. And yeah, generally for most concentrations, you dump it in, and then you'll find that you get a precipitate. Obviously, some dissolves because it's an equilibrium, but you'll often get a precipitate. Now, the point I'm trying to make here is if you, for some reason, need to figure out if something is soluble or insoluble, if, for example, for module 8, right? You know, you want to figure out what your, you know, anion or cation you're adding in to, you know, to solubility. And you can't remember your solubility rules, although you should. So try to remember them in the first case. But if you, as a backup, if you've forgotten and you need to work out if something is soluble or insoluble, then basically what you can then do is you can look up the reference sheet if it's on it. If you've got a KSP quoted on your reference sheet, you can basically say it's insoluble, all right? Your reference sheet has a whole bunch of compounds listed there. None of them are soluble. All of them are like 10 to the minus, you know, I think 10 to the minus 4 is the biggest one. So they're all considered insoluble, okay? So if you can't remember, then, well, use what resources you've got. You've got the reference sheet, see if you can find it there. If you can find it there, then you know it's insoluble, you know. All right, so that's just the exam tip that I'm sort of giving you here. Now, your lead chloride 2 will give you that. Now, so we'll need to correct a mistake over here. This lead chloride, as I mentioned earlier on the previous slides, is actually representing a dissolution, so you should definitely be writing it as a solid. If that was aqueous, then my KSP wouldn't make sense either. It's because it's a solid, that's why we ignore it. And so we've got KSP of this. So you could be asked to basically, you know, we will do this, we will demonstrate this common ion effect sort of quantitatively, but let's think about it qualitatively first. And this we kind of already did earlier, but basically, you know, we're going to compare water versus, let's say, 0.1 mole per liter NaCl, all right? And basically, we'll compare the solubility. So let's firstly do it qualitatively first. So qualitatively, we've already said it, so I'll run through it very briefly. In 0.1 mole per liter NaCl, that means the chloride concentration has gone up, and therefore, by LCP, it will want to reduce chloride ion concentration, and therefore it will shift left, and therefore solubility goes down. So that's basically explaining the common ion effect using qualitatively, using Le Chatelier's principle to show that the solubility decreases. And that hopefully all makes sense to you guys. We will now confirm this quantitatively and, you know, give you guys a sort of an example of what we can sort of do with calculations. So we will calculate the solubility in water and in 0.1 mole per liter of sodium chloride. So we'll write it again. Now, if you're in water at 25 degrees Celsius, then we basically just, you know, we basically use a bit of algebra here. So if X equals, you know, 0.1, if lead X equals, you can either let it equal the lead or the chloride, it's up to you. Having said that, most people prefer using whole numbers and not fractions. So it's probably better to let X equals the concentration of lead, because we'll note that the chloride ion concentration is 2 times the lead concentration, which means it's 2x. If we do it the other way around, we'll end up with a half x, and you can do it, but most people prefer not having fractions. And so what that then means is, because KSP is, you know, lead times chloride squared, we're saying x times 2x all squared, which is 4x cubed. And remembering that this is 1.7 times 10 to the negative 5, you know, I won't show the working for that. You guys should be able to do that. But let me quickly grab a calculator. I'll be right back. Quickly doing some calculations here, we should find that x equals 2.06 times 10 to the negative 3. And so what that then basically means is that at saturation, the concentration of lead chloride is going to be 2.06 times 10 to the minus 3 mole per liter in water at 25 degrees Celsius. All right, so now let's do it in 0.1 molarity NaCl solution. So we will still let, you know, the starting is the same, so I won't rewrite it to save time. So we'll still let x equals that. Now, in this time though, chloride concentration is still 2x in the sense that you will still get, for every lead chloride that dissolves, you will still get 2, you know, times x. But the thing is, because you're in 0.1 molarity of NaCl, then, you know, and because NaCl, you know, gives you like Na plus plus Cl minus 1 to 1, then we're going to get 0.1. And, you know, if it was like, you know, BaCl2, then, you know, then I'll be adding 0.2. So you need to work out basically the chloride concentration that was already existing, right? That's already existed. In this case, there's 0.1 there already. And do remember that we're working in terms of concentration. I'm giving you concentrations directly. If they, you know, gave you other things like moles, then you need to, you know, obviously convert to concentration through liters, all right? So always deal with concentration here. So what that then means then, in this case, is that your KSP will end up being, well, you know, still lead times chloride all squared. And that's going to be, you know, x times 2x plus 0.1 all squared. Now, if you can just, depending on how good your maths is, but hopefully you can kind of see that, you know, this is x to the power of 1. This is, you know, squaring it, so you'll get a power 2 here. So this is a cubic. So chemistry, you're not really expected to just be able to solve any cubic, right? You know, not any x cubed plus bx squared plus cx plus d, all right? You're not expected to do that. And, you know, it's fairly complicated, and, you know, unless you have a particular cubic, you can't do that for any cubic. Yeah, well, unless, you know, your math is beyond year 12 level. So basically we make a simplification. Remember, x is the concentration of lead, which is how much dissolves. And this is always, you know, for anything that's, we're doing calculations like this, it's meant to be more or less insoluble, just only slightly soluble. So basically we assume x is small. So this is not exact, this is not an exact thing, but it's close enough, so, and it makes things a lot easier. So we're going to assume that 2x plus 0.1 is basically 0.1. Because if you think about sort of like, you know, I mean, I picked one that's relatively soluble, so the difference is slightly bigger, but often, you know, even then, this is like 10 to the minus 3, which is still like, you know, 100 times smaller, roughly, compared to 0.1. So it's not a major difference, okay? But it makes a major difference to the simplification of the question. So now we'll get x times 2x all squared is now, not 2x all squared, but 0.1 all squared is going to be 1.7 times 10 to the negative 5. And in other words, x will therefore be 1.7 times 10 to the negative Well, something's gone wrong for sure. Oh, right, I left that out. No, well, something is clearly incorrect here because we're meant to get an answer that is smaller than that. Let's quickly check if we can find a mistake here. So it appears we found the error. It appears that we made a calculation error when we were doing the calculator over here. And so that appears to be 1.62 times 10 to the minus 2, which is now, you know, minus 2. And therefore, this hopefully now is correct. So that's 1.7 times 10 to the minus 3 mole per liter. And then this now demonstrates quantitatively, we have now demonstrated the common ion effect. Because if you compare these two numbers, this is 1.62 times 10 to the minus 2, and this is 1.7 times 10 to the minus 3. We have now basically quantitatively shown that, you know, 0.1 molarity NaCl makes, you know, lead chloride less soluble for sure, because, you know, this number's gone down, you know, and in this case, by about 10 times. It's about 10 times less soluble. Now, and you have to remember, lead chloride is one of the more soluble ones. If we picked a more insoluble one, it would, you know, it could make a difference of 100 or 1,000 or even more times. All right. And so what the common ion effect is, as we've said earlier, is really just the fact that we're saying that when you have an ion, so, you know, in my example on the next page and here, I'm using sodium chloride. So sodium chloride is made up of a sodium, you know, sodium ion and a chloride ion. So, you know, NaCl solid becomes Na plus Cl minus. And in other words, this chloride ion is common to both sodium chloride and, in my example, lead chloride. It's the same ion. And because I'm essentially kind of, think of it like I'm adding chloride to this one. Basically, based on what we did earlier, we're adding chloride, so we're adding a product. And the common ion effect is basically by, you know, either adding or dissolving in a solution that has an ion that is common, then the solubility of this, you know, compound will go down. And as we've demonstrated both quantitatively and qualitatively and conceptually, lead chloride will be more soluble in water, which doesn't have chloride, right? Certainly not much. Whereas if you put it in sodium chloride solution, which does have chloride, because of this common ion, then the solubility goes down. And we've done that qualitatively here. That's our conclusion by Le Chatelier's principle, considering this, adding this, shift left. It's also our conclusion when we say, when we calculate these, we find that this number is low. Okay. And so, you know, calculation exam questions can you basically, I mean, there'll be sort of more or less twists or variations on this, but basically, you know, they could just ask you things like, you know, if you add, you know, X amount of grams of some compound into, you know, either water or, you know, some sort of solution. So, you know, solution M with concentration C, doesn't really matter. You know, they will say like, you know, will it dissolve? Will it fully dissolve? And that basically just depends on, you know, if it fully dissolves, does it reach K? If it doesn't, then you know, it can still dissolve. You know, or will it, you know, be fully, you know, will it create a saturated solution? Or it might, you know, ask you like, you know, if I have a saturated solution, you know, and I add, you know, some, you know, ion, some sort of ion. So this will be a common ion. Otherwise, there's not much point asking the question. What is the solubility of the compound and how will it change? So just giving you sort of example question. More or less, we do them all the same way, essentially, right? And, you know, note that you don't have KSPs for anything outside of 25 degrees. So they could also ask you things like, you know, they could either ask you qualitatively, in which case you just rely on Le Chatelier's principle, or they could ask you quantitatively, in which case they would have to give you the information. They might say something like, if I increase the temperature, or, you know, they might just give you a different temperature. So temperature equals, let's say, you know, 60 degrees Celsius, as an example. What happens to the solubility of the compound? Now, if you're doing this qualitatively, you just need to know if it's X or endo. If you're doing this quantitatively, you will need KSP. And this must be given to you in the question somehow. Because you only have KSPs for 25 degrees Celsius. The reference sheet only has 25 degrees Celsius. So they might have changed the temperature to 60 degrees, and they might have given you a KSP, but the steps don't change. You're doing the same thing, but with the KSP they gave you, all right? Good, well, that's basically module 5. Does anyone have any questions?